Hello again. This is the second lesson on exponentials and logarithms for year 12, in other words the AS part of a full A-level course. Here we're going to have a look at differentiating e to the power x and similar functions, and also sketching some exponential graphs. But we'll start off as ever with a warm-up of 4 questions. Here they are. 1, 2, 3, 4. I'd like you to copy these down if you can, then attempt them, and then only play the solutions when you're ready. Or if you can get a printout of this, even better, but only look at the solutions after you've attempted them. You won't get any benefit from just copying out my answers. Okay, so when you're ready, pause, then press play when you want to see the solutions. Okay, so here they are. Question 1. Solve the equation root x plus 10 over root x equals 7. This is not particularly obvious to see what to do with. What you need to do here is to think that this might be what I've called in the past a disguised quadratic. So it can be manipulated into a quadratic equation, but you just wouldn't think it looking at it now. So we need to make a substitution. So what I'd suggest is introduce big X in place of square root of x. What that gives us now is x, big X, plus 10 over big X equals 7. Now we can now manipulate this into something which we can solve. So if we multiply both sides by x, we get x squared plus 10 equals 7x. Bring all the terms onto the same side of the equation. We then have x squared minus 7 lots of big X plus 10 equals 0. And now this will quite obviously factorise into x minus 5 and x minus 2 equals 0. We can now solve this for big X. So this equation is going to be solved when either bracket is equal to 0. And so therefore what we can say now is either big X is going to be 2 or big X is going to equal 5. But of course you need to remember that big X is just the square root of little x. So we can change this and say, but because big X equals root x, if we square both sides, we can then say that little x is the same as big X squared. And so if we take these solutions here, but then square them to get what our little x is, because this is an equation in terms of little x, we then get that little x is either going to be 4 or going to be 5 squared, which is 25. And that is our full solution. So it's quite hard until you spot that it might be a hidden quadratic. Question 2. First part, factorise completely x cubed minus 6x squared plus 9x. So in order to do this, we notice there's an x term in each of these, so we can take that out immediately. And we get this. Now this bracket here will factorise as well. Two numbers that multiply together to give positive 9, when we add them to, we get negative 6, that's minus 3 and minus 3. And so this is going to be brackets x minus 3 all squared. This is a cubic though, so we need to remember when we're sketching it for part B, it will have the same characteristic positive cubic shape, which will be something like this. We need to consider where it's going to be equal to 0, this function. Well, it's going to be equal to 0 when x is equal to 0. And because here x equal to 3 is a repeated root, the graph will bounce, as it were, at x equals 3. And so the graph, fitting through these points where this is going to be a repeated root, will have to look something like this. It comes down again and back up. It does say to label where it meets the x-axis, so we need to label this 3, and that there obviously is 0, so that will do us. Question 3, I'm going to use our answer to question 2 to help us. From question 2, we had y, which I'm going to call f of x, which was x to the power cubed, x cubed, then it was minus 6x squared plus 9x. Whereas here, if I call this function something else, we can then compare f of x to this one. So if we have a look at question 2, our function x we cubed, then minus 6 lots of the input squared, then added 9 lots of the input. If we now compare the input here, x, and what's happening to it, with x minus 2, it's exactly the same function. It's exactly the same thing, but x has been replaced with x minus 2. And so this thing here, the equation we need to graph now, must be in fact the same as the function of x minus 2, because x has been replaced with x minus 2. So we need to remember our graphical transformations. To go from f of x to f of x of minus 2, it's actually a translation of positive 2 units in the x direction. Remember, when the change happens inside the brackets, it works in the opposite way to what common sense would tell you. So rather than subtracting 2 from each x-coordinate, we add 2 to each x-coordinate. Before, we had the x-intercepts were 0 and 3, so we add 2 to each of those. 0 plus 2 becomes 2. 3 plus 2 becomes 5. So we've got intercepts here at 2 and a repeated root at 5. And so the graph here is going to be something like this. Starts low, comes through at 2, and bounces a repeated root at 5 before going up again. Not the best sketch in the world, but good enough so you get the idea of what's going on. Finally, question 4, the now infamous or famous calculus corner. We've got to, for this one, differentiate f of x. So we're told what f of x is, we need to find f dashed of x. First of all, f of x isn't in the easiest form to deal with. So let's see if we can simplify this down slightly. Let's square out the top, and also we can replace the root, the third form, with an index form. So here, if we square this bracket, we'll have 3 squared, which is 9. Double the product, so 3 times minus 4 is minus 12. Double it, that'll give us minus 24 lots of root x, which is x to a power half. And square the last term. 4 squared gives us positive 16. Root x all squared just gives us x. And all of that is going to be divided by square root of x, which is the same as x to the power of a half. So if we divide through all the terms on the numerator by the denominator, we get 9x to the minus half minus 24. The x to the power half on the top cancels with the x to the power half on the bottom, so we're just left with 24. Then we have plus 16. X to the power 1 divided by x to the power half. When we divide, we subtract the powers, so 1 take a half just leaves us with x to the power of a half. So that's f of x. So now we can differentiate this to get f dashed of x. So what happens here, I'm going to do it in descending power order. So starting with this power here, because that's the highest power of x, the power comes to the front and multiplies this term here. So a half times 16 gives us 8. And we subtract 1 from the power. So half take 1, it gives us minus a half. And over here, again the minus half comes to the front and multiplies this constant, the coefficient. So 9 times minus a half gives us minus 9 over 2. And again we subtract 1 from the power, so minus a half minus another 1 gives us minus 3 over 2. And so that is the derivative. I've not done it very straight, but never mind. Part B, evaluate f dashed of 9. I'm going to show you the long way, then I'm going to show you the cheat calculator way, which you might be a fan of. So f dashed of 9, we just simply input 9 into the gradient function. And so 8x to the minus a half That's going to be 8 times 1 over 9 to the half, which is the same as 1 over the square root of 9, which is 3. And again, you can use a calculator to do these directly if you'd like. Going over here, we're going to have minus 9 over 2 times 9 to the power minus 3 over 2. And in fact, I'll just show you using a calculator, just doing it the slow but steady way. And so 8 multiplied by 9 to the power of minus a half, then minus 9 over 2 minus 9 over 2 multiplied by 9 to the power of minus 3 over 2. And that should give us a value of 5 over 2, which is the same as 2.5. So we can leave it as 5 over 2, and that's absolutely fine. If you write 2.5, that's okay, as is 2.5. I did mention a way you can use, which is a bit of a cheat. I'm going to show you how to do this on the calculator. So this calculator has a function which is particularly powerful. If we press Shift and then the integral button, we can then differentiate continuous functions at any particular point for x. So we can type this in exactly as it looks without having to manipulate anything at all. So it's a fraction, as you can see. So up the top, type it in exactly as it looks. Bracket 3 minus 4 square root x. So we do square root button, alpha right bracket, scroll along, close brackets, and then all of that squared. Scroll down, and then the denominator needs to be root x. So square root alpha right bracket. We now need to input where we're evaluating this gradient function. So this box here, we need to put in 9. And what do you know? We get 2.5, which is exactly the same as 5 over 2. So that's a much easier way. If an examiner asks you to show an algebraic method, you must do this. But if he doesn't, or she doesn't, or you just want to be quicker, or just check your results, this is a really powerful method. You should know this. So, okay, let's go on to the main bit of this lesson. Like I mentioned at the end of last session, the number e, where e is between 2 and 3, is a special number where the gradient function of the exponential function f of x equal a to the power x is exactly the same as the original function. It's an infinitely long non-recurring number, just as pi is. So to 50 decimal places, this is the value for e. Last lesson I introduced it as being 2.718 to 3 sig figs. So this is going to be a number that crops up again and again in your A-level study. Formal definitions of e. I've given you the two main ones here. And so this is an infinite summation where e is a sum from n equals 0 up to infinity of 1 over n factorial. Okay, so the more terms we have, the closer to 2.718 we become. And this one here, another definition of e, is in terms of a power series. It's the sum of 1 plus 1 over n, all to the power n, as n gets increasingly large. Apologies, I don't mean to say power sum. I mean, it's an expression where as n gets closer to infinity, we can just substitute in bigger and bigger values, and this becomes closer and closer to the value for e. The main property of e is that when a equals e in this function, the derivative of a function is identical to the function itself. So when we're differentiating e to the x, we just get back the exact same function. So if f of x is e to the x, f dashed of x is again exactly the same thing. I wrote it here in dy by dx form. Another thing as well is if we adapted e to the x and called it e to the kx, similar to normal differentiation, if we didn't differentiate this, where we have a constant before the x, the constant term comes to the front and multiplies any coefficient we have. So in this case, there's no coefficient. If there were, the k gets brought down and multiplies any coefficient in front of the e. So we're going to show you this with a few examples. So first of all, differentiate y equal e to the power 4x. So this one here, all that happens is the 4 gets brought to the front of the function. So dy by dx, this 4 gets brought down, we have 4e to the 4x. So that's it for part A. Make some space. Part B, we've got this function here, exactly the same idea. Because it's in fx notation, I'm going to do this as f dashed of x. The coefficient gets brought to the front, so the minus a half comes here. And then the power gets left exactly the same, and we have e to the minus a half x. For part C, again, similar idea, but now we do have a coefficient in front of this e, which is 3. Same idea applies. The coefficient of the x in the power still gets brought down to the front, but now multiplies the coefficient at the front. And so this minus 5 gets brought down and multiplies the 3. So dy by dx equals 3 times minus 5, so minus 15. And yet again, this power gets left alone. So we get minus 15 e to the minus 5x. Question 2. The function f is defined in this way, so this is a slightly different one, going slightly beyond the scope of the exercise you're going to do later. F of x equals e to the 5x plus 3, where x is a real number. First of all, we need to find f dashed of x. So again, I'm going to give myself some more space, just divide the page in half. So you might notice that I've not mentioned anything like this. I've mentioned if it's e to the kx, but here I've got a constant added on. So for part A, I'm going to introduce you to the general idea in a moment. So rewrite f of x in terms of laws of indices. So remember, when we multiply indices of the same base, we add the powers together. And so this expression here is the same as e to the 3 multiplied by e to the 5x. Okay? So that's exactly the same thing as what we had written in the question. But now we can use this to our advantage. Using the same idea as before, if we find f dashed of x, the power here gets brought to the front. And so the 5 gets brought down to the front and multiplies any coefficient in front of the e. Now, as you can see in front of this e, is this constant term here. This is just a constant because it's got no x, y, or any other variable in it. So 5 gets brought down and multiplies this thing. So we have 5e to the 3. And again, as before, this power stays the same. But now we can reconcile these powers. So we have 5 times e to the 3 times e to the 5x. So we can put these powers together into 1 yet again. We have 5e to the power 5x plus 3. So if you look here, if you were to differentiate 5x plus 3, we'd just be left with 5. And so the 5 gets brought to the front, and this function of x, which is the power itself, gets left alone. So this tells us another result, which we're going to do in depth in future, but not right now. But just to explore this for the more curious of you, the general rule is, if we have y equal to e to the f of x, then dy by dx, give myself a bit more space, dy by dx is this derivative function here gets brought to the front, and the power, if it's a function of x, gets left exactly the same. So it might be worth remembering. Don't worry about it now, but that's the general rule. Anyway, part B. Find the gradient of a tangent to the curve y equals f of x when x equals 0.2. So for part B, we're just evaluating f dashed at 0.2. So f dashed of x from before was this. So we just need to substitute in x being 0.2. So we get 5e to the power 5 times 0.2. 5 times 0.2 is just 1 plus 3, which is obviously just 5e to the 4. And if you wanted or needed to give this to a certain number of significant figures or a numerical answer, we could key this value into our calculator. So we do this by doing 5, then alpha, the standard form button, then to the power 4. And to 3 sig figs, this would be 273. Pretty steep, basically. Again, I'll just show you briefly how to cheat the system, if you'd like to. What we can do to work out the gradient is use this gradient function on the calculator. So if we press Shift and then this integral button, we can type in the function we want to differentiate, in this case, this thing here. So press alpha, standard form, to get e, then to the power of 5x plus 3. And we're differentiating this function when x is 0.2. So if we scroll along and type in 0.2, we get the same thing. So this really is a powerful function on your calculator. If you know this, you've really got a massive advantage in the exam. Next up, sketching the graphs of exponential functions. The main thing here is you need to remember we're sketching. We're not being deadly accurate, so don't waste time, redoing the sketches time and time again. My sketches, as you know me by now, are absolutely rubbish. But as long as they're good enough, you'll be okay. I'm going to show you what would pass. First of all, we've got y equals e to the 2x plus 1. So here are a couple of axes I made earlier. What I would suggest doing is just read the question carefully and note where it says any point where the graph crosses the axes, okay, and also equations of any asymptotes. So if you're not sure, by the way, use your calculator if it's an exam, try different values. If you're not in an exam, use your calculator and a graphing piece of software, for example, Desmos or GeoGebra. The main thing here I'd draw your attention to is when x is 0, when it crosses the y-axis. When x is 0, y is going to be e to the 2 times 0 plus 1, which is e. So it's going to cross at 0, e. And so this is going to be e. And if you can remember from last lesson, as the power of e gets smaller and smaller and approaches negative infinity, y just gets close and close to 0, but never actually touches 0. I'm hoping you'll see it's more obvious that when this power gets bigger, it's going to shoot off towards infinity. If you don't believe me, like I say, use your calculator. So if I just type in alpha e and put a massive value in, a massive negative value in, sorry, that's a bit of a light, it's been rounded to 0. If I try something a bit less, look, minus 5, minus 44, it's going to get so close to 0, but it can never get less than 0. And so an asymptote here is the line y equals 0. So you've got an asymptote at y equals 0. Basically the x-axis. Oh, this makes me nervous. I'm going to try and sketch it now. I'm awful at sketching graphs. It's really steady and shallow, close to the axis, but eventually comes up and up and up. Crosses the y-axis at E. And gets steeper and steeper after. That is absolutely horrible. That's incredibly wonky, but The examiner would maybe have a bit of a smirk, but would actually see what you're trying to do here. That would actually be okay, as awful as that looks. If you want a smooth version, have a look at GeoGebra or Desmos, as I say. But the general idea is as this gets towards negative infinity on the x-axis, it gets close and close to 0. As x gets bigger and bigger, this graph will shoot off at an increasingly rapid rate. Sketch B, y equals 10 e to the minus x. Okay, so this one here, we've got a coefficient of e, which is 10. And so when x is 0, let's just think what's going to happen. When x is 0, y is going to be 10 e to the minus 0. Anything to the power 0 is 1, so that's just going to be 10. And so it's going to cross at 10. And e to the minus x, if you remember from last time, is actually going to be a reflection in the y-axis of a graph of e to the x. And again, if you're not sure, try some values in on your calculator. So for example, if I were to try 10e to the power minus 1, 3 point something, minus 2, didn't mean to do that, increases, so it doesn't increase, it goes to 1.3. (10e to the minus 3). It's going slower, lower and lower. So what's going to happen here is x gets bigger, the graph will get lower and lower, will approach 0, until eventually have something like when x is 100, it's really, really low. Whereas if x is a negative number, because it's e to the minus x, what we'd have is e to the positive number. So for example, when x is minus 5, that'll be 10e to the power minus 5, which is going to be pretty huge. And so the graph is going to be massive over here, but approaching 0 as x gets bigger and bigger. So the graph is going to look something like this. Apologies if this sketch goes a bit wrong. That's not too bad by my standards. So yeah, there's an asymptote again when we've got x going towards infinity. So again, there's a asymptote at y equals 0. Again, another asymptote on the y-axis. Final one to sketch is part C, where y equals 3 plus 4 e to the half x. So let's get the axes and try and sketch this one. So again, I'd suggest to try when x equals 0. When x is 0, y is going to be 3 plus 4 times e to the 0. E to the 0 is just going to be 1, so 3 plus 4 times 1 will be 7. So it's going to cross the axis here when y is 7. And as well as that, there will be an asymptote as ever. However, in this case, we've got this plus 3 to contend with. And so, obviously, as x gets bigger, the graph's going to shoot off, going higher and higher as x gets bigger. But as x gets smaller and smaller, 4e to the half x is going to shrink down towards 0. So as x goes, in fact that might be in the way of the curve, I'll write this somewhere else. I'll write this over here. So as x gets smaller and smaller and smaller, the 4e to the half x bit is going to get closer and closer to 0, but you're still always going to have this 3 left. And so y is going to go closer and closer to 3. So in other words, as x gets smaller and smaller and smaller, the function of x, y, is going to approach 3. So there's going to be, again, a horizontal asymptote, this time where y is 3. So again, sketching this graph in. Down here it's going to be very small. Getting bigger and bigger and bigger. Terrible. I can't apologise enough for how bad I am at sketching curves. But anyway, that's the general shape. And so an asymptote horizontal at y equals 3. And it's going to cross the y-axis when x equals 7. So horizontal asymptote at y equals 3. And that's essentially it, really. It's now over to you to try some of these yourselves. So if you can turn to page 316, exercise 14b, and try questions 2 through to 4, then move on to questions 5 through to question 8. That gives you practice with both differentiating the exponentials and also sketching them out as well. Try those now. If you have any trouble, do leave a comment for me or send me an email back and I'll endeavour to help you if I can. If I don't get back to you, email me again because I might have forgotten. Thanks for listening if you got to the end, and you'll hear from me again soon. See you for now.